last week we introduced and explained the concept of moments, right? Now I talked about moments, I talked about the whole thing about rotation, potential for rotation, but I never actually explained why we're using moments. If you remember from last week, we did a bunch of examples where we calculate moments, but we're never actually told why, or you're never actually told why. So today, hopefully, we'll answer that question. So today's topic is Chapter 5. And if you have already read your notes, you'll know that Chapter 5 consists of equilibrium, right, of a rigid body. And what does that mean? In previous chapters, particularly in Chapter 3, we looked at equilibrium of a particle, which means that we studied all the forces acting on a particle. A particle, as you may remember, has mass, but no discernible size. Now in this class, we are going to change all that, and instead of looking at equilibrium at a small particle, right, we're going to look at equilibrium at an entire body. And there's a reason for that. You see, we mentioned that last week, we mentioned that it's not just important to know the direction of the force, we need to know the location. And the reason we want to know the location of the force is because where that force is located is going to result in a rotation. Okay? So for example, if we had this beam and we applied one force here, maybe one force here, can you visualize how these two forces would cause a rotation? Yeah. These two forces would cause a counterclockwise rotation. And the reason we were studying these locations of forces was to quantify them with what we call the moment. Now we're going to hopefully get everything that we learned on last week and apply it, right, to our study of static systems. So when we studied static systems, we said that we had three main equations of equilibrium, right? We had that the sum of forces in the x direction equals 0, the sum of forces in the y direction equals 0, the sum of forces in the z direction equals 0, but I said that we're missing one. Now if you have forces acting on a body, you can quantify the linear force and balance them. But we said that if your forces are displaced from each other, they will cause a rotation. So in order for a body to be fully static, right, that is not translating linearly, not moving linearly, and not rotating, we need one more condition of equilibrium. Does anybody know what that condition is? That's correct, right? So in addition to the forces equaling 0, the moments on a body have to equal 0. And in order to study the moments of a body, we need to look at bodies as a whole and not just simplify them as particles. And that's what this entire week is all about. This week we're going to focus on equilibrium of rigid bodies, which means we will take a body and then we will try to apply the equations of equilibrium to that body. Hopefully, we are ready to start. Now, when we're looking at rigid bodies, we need to look at them from an engineering perspective. Now, when I say from an engineering perspective, it's because we're not just trying to come up with theory here. We're not just trying to come up with relationships and equations and definitions. We also want to see how we can apply what we're learning here into our field. Now, the first thing I would like for you to always visualize is in engineering, your rigid bodies are never in a vacuum, right? You're never studying an individual body that has no relationship and no connections to anything else. So when you're studying a rigid body, you have to consider, its surroundings. And the reason you want to consider its surroundings is because the surroundings of the body will determine part of the forces required for equilibrium. So let's say, I'm just going to give one example. Let's say that we're looking at this crate. Okay? Crate is being lifted up. And let's say, right, that as this crate is being lifted up, most of the contents inside the crate kind of like slide off to one side, okay? So all the contents inside the crate are pretty much gathered on one side of the crate. If I now want to consider the force of the weight of the crate and its contents, where do you think that weight will act? Will it still be a weight acting at the center of the crate like we would normally have? No. Where would it act then?
To the right.
More towards where the contents are gathered, right? Okay. So we're going to have a gravitational force acting pretty much where the contents are gathered. I hope that you can now start to see why this is important. Because if the weight, right, is gathered to one side of your crate, then what's going to happen here is that the forces that are lifting the crate cannot be equal. Because if the forces are equal and the weight is not centered with the forces, then we have a moment and we're going to have rotation. So when we're studying systems, like I said, it doesn't only matter the direction of the force. We also care about where this force is located. Because the location of this force is going to affect all the other forces acting on the system. In this case, if my weight is more tended towards the right, and I want this to be a static system, that is, I want my system to comply with all of these four equations, which of these forces do you think will have to be larger? Which of these two forces?
The one on the right.
Exactly. If I want to balance my system out, the force on the right will have to be larger than the force on the left in order to prevent this moment. So if I were to select a centroid of my area, and I'll explain what centroid means later, but if I were to select, let's say, a geometric center point of my system, and I want to find the moment around this center point, then we know that this force needs to counteract the moment from this force, because this will be a clockwise moment, and this will be a counterclockwise moment. What that means is that now this force has to be bigger than this force. So here's where equilibrium of rigid body comes into play, where we need to consider rotations around the body. Now, of course, bodies don't act in a vacuum. So just as our crate is connected to an outside, so an external environment through these two cables, we have bodies that can be connected through multiple types of supports. In this class, we're going to simplify our supports based on how many reactions they exert in the system. So when I say reactions, what do you think I mean? What do you think the word reaction means? So Newton's third law of motion. For every action, there's an equal and opposite reaction. So what is reaction?
The response to action.
A response, right? A response to an action. For example, if I were to punch the wall, here's me punching the wall, I am exerting a force on the wall equal to the magnitude of my punch. But if the wall doesn't move, that means that the wall is exerting on me a reactive force. Now, how do you calculate reactions? Well, Newton's third law of motion tells us that for every action, there's an equal and opposite reaction, which means that if our system is static, then for every action occurring on the environment should supply an equal but opposite reaction. So let's look at an example of that. Let's say that I have, and I'm going to try to simplify everything in terms of beams, because I think beams are easier to look at. So let's say we have a beam, and this beam is mounted on two rollers. What this means is that the beam can move freely from side to side, but of course the rollers will prevent it from falling down. My system here, okay, what I'm studying is my beam. This is the rigid body I'm looking at. Everything outside of that rigid body is the environment. Now in this case, just looking at the system, ignoring everything outside the system, do you see any forces? Or can you think of any forces?
Gravity.
Gravity, okay? So we have a force of gravity. Now if I were to look at this beam in a vacuum, I can only see one force, and my system is not static. But in order for this system to be static, there needs to be a reactive force, a force that balances out your sum of forces, right? So that it can be equal to 0. Where do you think those forces are coming from? The supports, right? The rollers. which means that we can't look at our systems in a vacuum. We always need to consider the environment. And if our system exerts a force on the environment will exert an equal but opposite reaction that will keep my system static. Does that make sense? This is the first type of reaction of support, that I would like for you to study. These are what we call rollers. And rollers, notice that they can only provide a reaction normal to the surface they're in. So if my surface were, let's say my beam is just resting on the floor. If my surface were diagonal, the reaction would be normal to that surface. So I don't want to say that rollers can only provide an X force or a Y force. Really, they just provide a force normal to the surface, and whether it's X or Y depends on the inclination of your surface. There's a second type of support that we're going to study, and again, think of these as simplified supports. The second type of support is what we call a hinge. Now, you've heard this word before, so what do you think a hinge stands for?
The point about which the thing rotates.
Exactly. In other words, when we're looking at a hinge, the beam can rotate freely. The beam can rotate around a roller freely if it wanted to. So with a hinge, the beam can rotate freely, but it cannot move linearly in any direction. So hinges will have a reaction force in the X direction and a reaction force in the Y direction. I can't say the same thing about rollers because rollers can really depend on the inclination of the surface. In this case, it's only a Y reaction force. In this case, it's an X and a Y reaction force. But hinges always have reaction forces in the X direction and in the Y direction. Now, we've looked at two different types of supports. And these supports are preventing linear displacement. What other reaction do you think we need to account for? We're looking at linear displacement, so okay, our supports can prevent this linear displacement, but is there any other type of reaction that we need to account for? Moment, right? So we're going to define a fixed support. Think of a beam being placed directly into a wall. A fixed support will be one that doesn't prevent any linear movement and does not prevent any rotation. Which means that my fixed supports are going to provide not only an X and a Y reaction, but also a moment reaction. So those are the three types of supports that we are going to study today, or in this week. Rollers, which provide a reaction normal to the surface. Hinges, which provide a reaction in the X and Y direction. And fixed supports, which provide reactions in the X and Y direction, in addition to a moment reaction. Now, as you know, I like to say, the best way to apply this is to try an example to see if we understand this. So let's go ahead and work with number 5.1. It's a very easy one, and I'm glad that it's easy because they will help us look at this so-called equilibrium of a rigid body. So in example 5.1, we have a beam that is connected to a wall. Okay? Now this beam is static, means it's not moving. The mass of the beam, I'm just going to write it here, the mass is 100 kilograms. And there is a force of 1,200 newtons acting at a distance of 2 meters from the wall. Now the beam itself is 6 meters long. So given all this information, I would like to know, what are all the forces in my system? In this case, my system consists of the beam. But remember, we cannot look at this beam as in a vacuum. We need to consider all the forces that are acting on the beam, even those from the environment.
So we got a moment, right?
All right, let's take it step by step. When we're looking at equilibrium of a particle, what was the very first step we would take in solving those problems? Before we identified anything.
Free body diagram.
There we go, free body diagram. So when we're looking at equilibrium, remember, first step will probably be to draw a free body diagram. In this case, my free body diagram is of my beam, that's the system, and it has to include all the forces acting on it. Now remember, when we did particles, we would have our x-axis or y-axis, and our particle was always at the origin. All the forces acted somewhere towards the origin, towards or away from. But here, we have a body. So it's not just a particle. I can set my origin wherever I want, but I do need to understand that now that we're looking at a body, it matters where the forces act on. So looking at the system, what's the first force that you can identify?
The 12,000 newtons.
Okay, 1200. 1200. So you're at 1200 Newton force. And that force is located at 2 meters from the left. I'm just going to set my origin to be perhaps here. Just as a decision I want, okay? Remember, I mentioned a few weeks ago, the free body diagram should tell me everything I need to know to solve this problem. If everything I need to know is not here, then it's not a good free body diagram. So what else do we need? What other forces can you identify?
Weight.
Exactly, weight. So we have a beam with a mass of 100 kilograms. What's the weight of that beam? 100, that's kilograms, that's mass, times acceleration of 9.81 meters per second squared, 981 newtons. But where does it act on?
The y-axis.
Okay, along the y-axis, but where? Yep. Now here, I would like for us to be a little bit generous. We're going to explain later on what the center of mass is and how to find it. But for now, because I want to focus on moments and reactions, let's assume that my beam is homogeneous and uniform, which means that the weight always acts at its center. Now, that doesn't mean that the weight will always be at the center of every object. It just means that for the next couple of weeks, we'll deal with these uniform bodies whose weights act on the center. I'm going to try to draw this a little bit more to scale. Just a little bit. And we mentioned it's 1200 newtons at a distance of 2 meters. We mentioned that the weight of that beam was equal to its mass, that's 100 kilograms, times its acceleration, which is 9.81 meters per second squared. That gives me a weight of 981 newtons. But remember, the free body diagram needs to tell me everything I need to solve this problem. So I have the force, I have the direction. What else do I need in order for this weight to have all the information? Yeah, the location, right? We have the magnitude, we have the arrow that gives me the direction. We also want the location. So where, if I'm setting my origin to be at the left of the beam, where does it act?
3 meters.
Yep, halfway through, so 3 meters. So what we have is a system where I'm looking at body forces. I'm looking at a surface force or impact force. But right now, if I look at it, this doesn't really look static. I have two forces. They're all pushing this beam downward. But this is a static beam. So what am I missing now?
Reaction force.
Reaction force, right? That's a key word, right? Reaction. Good. So we're missing reaction forces. Right now, this beam, as you can see from the diagram, is supported at the left with the wall. What type of support do you think this is? Fixed. Okay, good. What that means is that a fixed support will provide us with an R reaction, an X reaction, a Y reaction, and a moment. So that means that we will have to consider an X reaction force, a Y reaction force, and a moment. Now, it doesn't matter if you decide that the X reaction force is in one direction, the Y in another, because if you assume incorrectly, you'll get a negative answer. So I wouldn't worry too much about that. I mean, if it makes it easier for you, set your Y to be always positive to the up, your X to be always towards the right. But sometimes we can make a couple of informed decisions, right, just by looking at the system. Notice that we have two forces pointing directly downwards. So in order for this beam to be balanced in the Y direction, in which direction does my reaction have to be? Upwards. Yeah. Notice that we actually have no X reaction, or no X force. So we don't really need an X reaction. I'm going to write it down anyway so you can see why I say that we don't need it. And finally, we have a moment. And once again, we have two forces exerting a moment about this point in one direction. So in which direction should the reaction be? Counterclockwise, to counteract the effects of the moment from this force. Again, you don't have to assume correctly, because once you solve it, if you assumed incorrectly, you just get a negative value, and then you know, okay, my direction was incorrect. I'll fix it. So this is my free body diagram. This has everything I need to solve this problem. And what is the problem? I would like to know all of the forces acting on this system. Now you already found one force, which is the weight. Good, you found it. But now we can find our reaction forces, right? So how can we find the reaction forces? Well, if this is a static system, we apply equilibrium. Sum of forces equals 0. And just to give a little bit of an illustration on why the x-axis goes to 0, let's just start with the x direction. Sum of forces in the x direction equals 0. Looking at the system, what x forces can you identify? Just Rx, right? Okay, so I get negative Rx, negative because it's pointing towards the other side, equals 0. Therefore, my x reaction is 0. Again, you don't have to go through this process. If you can identify that there's no x reaction, then good for you. But you should know, as soon as one of these forces is inclined, there will be an x reaction, okay? All right, let's move on. Let's look at the y direction. Sum of forces in the y direction equals 0. What forces can you identify in the y direction?
Is that applied in the gravitational?
Okay, we have the applied force and gravitational force, okay? We have 1,200 newtons. Is that positive or negative? Okay. We have 981 newtons. Is that positive or negative? That's correct. And are those all my forces in the y direction?
There's also the RY.
Okay, we have a reaction force. And is that positive or negative?
Positive.
Okay. And all of this equals?
0.
Okay. So we get that my reaction force Ry is equal to 1,200 newtons plus 981 newtons, or simply, how?
2181.
Sorry?
2181.
2,181 newtons. Can we agree on this? Okay. My Rx is 0. I'm not even going to write it down. I'll just erase it from my free body diagram. My Ry is 2,181 newtons. We don't really have a z-axis, so we don't have to worry about axis. But is that all we need to prove that this system is in equilibrium?
No.
What else do we need? That is correct. Thank you. So we finally use our last equation of equilibrium. Sum of moments equals 0. And remember, to find moments, you need to find the point at which it is applied. In this case, I'm going to start at my origin. So sum of moments about my origin has to equal 0. What moments do I have at my origin?
1,200 times 2, 3 times negative.
Okay, good. So you're absolutely right. Let me take it from left to right so that everybody's on the same page, okay? Let's start from left to right. We have a reactive moment, okay? And if we're setting our counterclockwise as positive, then I can say that my reactive moment is positive. Is that correct? It's already a moment, so you don't have to multiply by anything. It's already a moment. It's already a rotation. We have a force Ry. At which distance is the line of action of this force acting from the origin? So what's the moment that this force causes about the origin?
0.
Okay, so we can neglect it. Remember, if your force intersects your point at which you're finding the moment, it doesn't cause a moment. And then finally, we have a 1200 Newton force at a distance of 2 meters. Will this force cause a clockwise or counterclockwise rotation? So is it positive or negative?
Negative.
And then we have a 981 Newton force at a distance of 3 meters. Clockwise or counterclockwise?
Counterclockwise.
Positive or?
Clockwise.
Oh. What do you say?
I said counter, but I get directions.
Okay. So clockwise. So
Yes, it's a negative.
there we go. Thank you. Are these all my moments in the system? What do you think? Am I missing something else? No. Okay. So all this equals 0. And now we can solve for my reactive moment. Reactive moment is 1200 times 2. That's 2400. Plus 981 plus 3. That's, I don't know, 2,942.
43.
43. Thank you. All right. So what is this moment equal to? The total thing. 2,943 plus 2,400.
5,343
Units.
Newton meters.
Thank you. Good. So what do we have? We have a system where we found all the forces, actions, and reactions in the system. All we had to do is apply the equations of statics, right? Sum of forces equals 0, sum of moments equals 0. And we have essentially, and here's where the term comes, we've solved the system. In other words, we found all the forces that make up this balanced system. Go ahead.
I'm a little confused about how that moment can exist. Isn't it 0 meters off of your origin point?
Yes, but this is already a moment. It's not a force. So hold this book,
Absolutely.
right? Hold it there. I'm going to apply a vertical force. Now, of course, to counteract my vertical force, you have to apply a vertical force as well. But notice that if you only apply a vertical force, the book rotates, right? It's inclined. Now hold it. Don't let me rotate it. Okay? Good. I'm applying a vertical force, but it's not rotating.
Correct.
So you're doing two things. You're applying a vertical force that's keeping it at its elevation. You're also, with your wrists, applying a rotation. Okay? So it doesn't matter where you apply the rotation. The fact that you're applying it means that the book is not going to rotate. Okay? So this moment is your wrists just rotating it. It has nothing to do with the force that you're applying it. So it's already a moment, right? So that's why we have to include it. Okay? So it is a force. It's just a different type of force. It's a rotating force, not a linear force like what we're used to. Okay? And here's you bring an interesting point. It doesn't matter where in the beam this moment is applied. We still have to include it in our equation. It doesn't matter where it is. We'll still include it. It will still be MR. So once again, if I were to give you the book, you can try to keep it from rotating. You can also hold it here and try to keep it from rotating. Of course, the moment that you have to apply is a reaction, right? Your vertical force may not change, but you're still applying a force with your wrists, trying to keep it from rotating. Okay? We can get into more details later when we actually start looking at more complex systems, but right now what we need to understand is that this reactive moment is always going to be part of your sum of moments equation, regardless of where the point is. Okay? Any other questions? Good. What's your name?
Daniel?
Are you good, Daniel?
Yeah.
Nice. Did we email today?
Yeah.
Nice. What's your name?
Oh, me?
Yeah.
Oh, yes, Luis?
The reporter?
Yeah.
Okay, good. Starting to remember. So Luis, Daniel, Sophia, Andy, Kevin.
Yeah.
Okay, Kevin, Tuong, Noah, Graham, Chris, Jared.
Yeah.
Nice. I actually heard him say it.
Yeah.
Someone else say it, but okay. Good. So let's do a couple more examples. And I'm actually kind of relaxed today because we're already halfway through our chapter. So we can actually dedicate the rest of this class to perhaps working on more examples. If we run out of problems, then we'll continue with our theory, right? Let's do 5.2. Okay. By the way, the examples that you're looking at in the book, they're only about drawing the free body diagram. They're not about solving them. So you may want to make sure you take notes, right? Because in the book, we're only getting up to this point. We're not doing any of this. But I believe in you. I know that you know how to solve these, okay? So let's do 5.2, okay? And in this example, what we have is this foot lever. You may want to look at it in your book because this one's actually going to be very hard for me to draw correctly. So find it in your book. And I will try my best to draw this system. See, I already started wrong. Okay. 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 So in this problem, we are given a foot lever. You press down on this pedal with your foot. And looking at these systems, right? Let's say that we have a hinge here. When you press down with your foot, what's happening to this side? What's happening to this side? If you're pressed down here with your foot, this is a hinge. Right. Yep. So you press down with your foot, you're exerting a counterclockwise rotation, and this counterclockwise rotation is going to result in these two elements being pulled. Is that okay? So it says that we have a foot lever, okay, where a vertical force is applied to the pedal. We'll call this F. So that the spring is stretched 1.5 inches, and the force on the link, which is this one, is 20 pounds. So I'm going to get, once I press down with a force F, I will stretch this spring 1.5 inches, and I will cause a force of 20 pounds on this link. Now, I'm going to give some dimensions. The distance between my spring and my hinge is 1 inch. Distance between the spring and the link is 1.5 inches. Of course, this is not drawn to scale, as you can see. The spring has a spring coefficient K of 20 pounds per inch. So this is for the spring. And the distance between the pedal and the hinge is 5 inches. Okay, So we have what's essentially a system with 1, 2, 3 forces, and however many reaction forces we can find. Now this system, of course, let's say that we balance this. This system, if we want it to be balanced, has to, right, has to have the sum of the forces and the sum of the moments equal 0. So then, how can we solve this system? Any ideas on where to start? We have a system, right? The first thing we want to do is what?
Draw a free-body diagram.
Yep. So I'm going to identify my system here. My system is this pedal. And my free body diagram should include that pedal, the forces acting on that pedal, and all the forces from the environment on that pedal. So I'm going to draw my free body diagram. I have my pedal. Okay. And now what forces am I looking at? Let's neglect the weight of the pedal for now. Okay, let's neglect the weight of the pedal itself. And what forces do we see acting on this pedal? We have a force from the foot, right? You press on the pedal, you exert a force F. What other forces do you see acting on the pedal?
The spring
Okay, a force from the spring. In which direction?
towards away from it, towards the wall.
Okay. So away from it. So we have a force from the spring. We're just going to call it Fs for spring force. What other forces do you see? We mentioned that when you press on this pedal, this link, let's say that it's also fixed or somewhat fixed, will exert a force of 20 pounds. Okay? So we have a force from the link of 20 pounds. Sophia, are those all the forces acting on the system?
No, there's also hinge.
All right, where?
The bottom right,
Okay. And what reactions does this hinge provide?
X and Y.
Okay. An X and Y reaction force. I'd like to say that it's safe to assume that the Y reaction force from the hinge is in the upwards direction. Do you agree? Okay, we have a Y reaction force down. It's safe to assume that my Y reaction force will be up. And I'm going to assume that my X reaction force will be in towards the left. Can we agree on that? Okay, good. Daniel, does the hinge cause or provide a moment reaction?
Yes.
You want to restate that?
Okay, no.
All right. Remember, hinges, by definition, they don't allow any movement, any linear movement, but they allow free rotation. And now my question is, if this system is static, what's this force F equal to? In other words, what's the force that the person pushing on the pedal is applying?
Or what? Oh.
But then what's our Y? I mean, you're not wrong, but what's our Y? It's not that easy.
It's a moment.
What?
It's a moment because it has a distance.
We need to consider moment. That's correct. So let's look at the step by step, right? We drew our free body diagram. Can we agree that this is a good free body diagram? The book is over there. I'm too lazy to go see the solution. Can we agree that this free body diagram is well drawn? Chris? Okay. Graham?
Yeah, I think so.
Can you do a better job?
Probably.
Yeah, you could. I agree. So can we agree that all the forces are here?
No.
No, there's a spring constant.
I have a spring force here.
Oh,
Okay.
There's also a moment
Where?
going along F. I'm not entirely sure, but I feel like something missing.
I feel like it's
So I'm going to restate the question. Can I solve this problem just by looking at this free body diagram?
Negative.
What am I missing?
distance.
Distances, right? So you're on the right track, right? We're thinking of moments, but what do we need for moments? We need distances. So I do need to include my distances. We have 1 inch. We have 1.5 inches. And we have 5 inches. And of course, you already know, as I've heard you try to say, we know that we need these distances because we want to consider moments, right? Okay. So now let's solve this system and let's find this force F. Again, the book kind of ends it here, but I want to actually find F. And I can start by applying my equations of equilibrium. So I'm going to start. My equations of equilibrium, sum of forces in the F direction equals what, Kevin?
X direction. Is that like gas force?
Equals what?
F of X.
You're too advanced for me. Just the general equation.
Equals 0.
There we go. I was about to throw something at you. You didn't get it, okay? Good. And then what forces do we have in the X direction? Let's see. Looking at this system, what forces can you identify in the X direction, Tuong?
All X.
Sorry?
All of X.
Okay. Because I'm drawing it towards the left, I'm going to say it's a negative force, okay? What else?
The spring constant.
Okay, spring force. And we're assuming that it's towards the right, which it is. We're not assuming it is towards the right. Therefore, it's positive. And what else? Okay. And all this equals? Okay, good. Good. So we have Rx, spring force 20 pounds. Can we find spring force? We're given the spring constant and we're told the deformation of the spring. So can we find spring force? I think we can. Now, this is not a class about springs, so I mean, you should know how to solve them. But really my point here is I want you to understand how to balance the system, right? So I'm just going to write it down. We have Rx. My spring force, my spring force will be equal to 20 pounds per inch multiplied by the displacement of 1.5 inches. Is that correct? Okay. Plus 20 pounds equals 0. That means that my reaction force Rx is 20 times 1.5, I guess that's 30, plus 20, how much is that? 50 pounds. Can somebody confirm that number for me?
Confirmed.
Okay, good. Now you may be wondering, why do we care about Rx if we want to find F? And you'll see why in a second, okay? So we found some forces in the X direction, and notice that all of my forces in the X direction are now solved. We have all the forces in the X direction. Luis, what now? We found the forces in the X direction. What now?
We can find the force in the y direction.
Exactly. We can find our forces in the Y direction. So I get sum of forces in the Y direction equals 0. Luis, again, what forces can you identify in the Y direction?
Force in the y direction is the force of the hinge, the reaction.
Okay, good. We have the force that we're looking for. That's our unknown. We have a reaction force equals 0. Uh-oh. We have a problem here. We get that our reaction force equals our force, but we don't really know what each of them are. So this equation, not very helpful for now. There is no z-axis. Are we done? Can we not solve it? Or is there anything we can do to solve this problem?
Moment.
Moment. Okay. So we get sum of moments equals what, Chris?
Or,
No, like general. You're too advanced. General. Sum of moments
General.
equals, there we go. You're too excited, right? And you want to finish the problem. And I'm happy for that. But give me the basics first, right? Sum of moments equals 0. Now, tell me what moments do you see?
20 times 2.5.
Okay, so let's go there. We have a force of 20 pounds, right? Acting at 2.5, but 2.5 inches from where? From the hinge, right? Okay. And I think it's safe to say, right, that the best place to find your moment is the hinge. Now, in addition to that it being a hinge, why do you think it's the best place to find the moment?
All our distances are given to that point.
Okay, all our distances are given to that point. Any other ideas?
it's an origin?
Okay, but why would it be our origin? Like, what does it help us? Think of it this way. When you find moments, any force that passes through your point, right, creates a moment of what? If the force is already acting on that point, what's the moment? What's the distance to that force if it's already passing on the point? 0. So what's the moment? So that means that if we set our moment at the origin, we have two forces that we can eliminate from the equation. So whenever you're choosing a moment, right, choose a point where you can eliminate as many forces as possible. In this case, that point is the hinge, because the hinge is the only point where you have two forces acting on it. So we can eliminate those two forces, okay? So set your moment at the hinge, because if you were to set your moment anywhere else, you would have one unknown Ry, in addition to an unknown F, okay? So set your moment at the hinge, okay? So I'm going to say my hinge is my origin. And Chris said that we have a force of 20 pounds acting at a distance of 2.5 inches from...
It would be negative.
Exactly, right? It will be negative because it's a clockwise rotation. Does that make sense, Noah? Clockwise, okay? Good. Noah,
Yes.
since I'm already bothering you, go ahead. What's the next moment?
The last one we solved for was the F.
So F?
What was the last one we solved for? The 20 pound one?
20 pound one, yeah.
Oh, okay. The next one can be the spring force.
Okay, so we already said the spring force was 20 times 1.5. I'll just write 30, okay? So 30 pounds.
Times the 1 inch.
Times what distance?
The 1 inch.
Okay,
And that is heading clockwise, so that would be negative.
that is correct. Graham?
The moment on the left is F, so it's F times 5. And it's counterclockwise.
So it's?
Positive.
No, this equals what, Graham?
0.
Okay. How many unknowns?
Only 1.
Can we solve for that one? So what is the force that you are applying on your pedal in order for the system to be static? That force will be equal to 20 pounds times 2.5 inches plus 30 pounds times 1 inch divided by 5 inches. So what is that force?
16.
Meters.
No, pounds. It's just pounds.
Just pounds.
Pounds?
There we go. There are no newtons here. This isn't even metric units.
Sorry.
I'm going to have to put a new rule in the test. It's like if the units are wrong, the question is wrong. And then when I grade, I only look at the units. Oh, that'd be
That's
funny.
fair.
Yeah.
Cool.
No. Good. Of course, if we know the force is 16 pounds, then what is the Ry?
16.
16 pounds. Good. We found all the forces in our system, Rx, Ry, our unknown force. So we can say that we have solved the system. Notice a couple of things. Even though the hinge does not provide a moment, right? There's no reaction at the hinge. The moments still have to equal 0 in order for the system to be static. So if the hinge itself does not provide any resistance to that rotation, then these forces alone must balance each other out. Okay? Any questions with this problem? This was a bit of a complicated problem, but I'm glad we did it because it is something that will definitely help us. Because it covers, we have spring forces, we have hinges, we have different directions, not different orientations, X and Y. But any questions? Let's see. Sophia, any questions with this problem?
No.
If this were on the test, could you solve it?
After a long time, yes.
But you have 5 minutes to solve the problem. Would you solve it?
Maybe.
Maybe. Okay, I like that attitude. You could be more confident. Kevin, you good?
I can't now.
Daniel?
I think after looking over it all along, maybe.
What do you think you have to look over? Let's just talk about it now. Let's see. Anything that you think is not really ringing any bells here? Or clicking? No, not yet? Okay, no problem. Luis, you good?
Yeah.
Can you solve this problem?
I can ask.
Okay, Tuong, Noah, Graham, Jared.
I did have a little bit of a question.
Mhm.
For extra clarification. So
Yep.
when solving for a moment, you don't have to have a axis assigned to any of the particular components of the moment, correct? So like,
Can you explain that again?
So-
Can you rephrase that for me?
absolutely. So in the case of our 20 pounds,
Mhm.
it's not exactly on the y-axis.
Mm-hmm. Yeah.
It doesn't matter in solving for the moment.
No, what matters is the location and the direction. So it doesn't matter if it's specifically on an axis or not, right? What matters is how far is it from your point, okay? And in which direction will it cause a rotation about that point? Okay.
Because it only matters perpendicular.
Yep.
To the location.
Yep. All we care about is that perpendicular distance to the line of action of the force. Remember, that was the key thing about moments, right? We only care about perpendicular distance to the line of action of the force. Good. I'm going to jump a little bit.
Before we jump,
Yeah, go
I
ahead.
have a question off of the stuff from last week.
Uh-huh.
It was on the latter questions with the average forces acting on the objects.
Mm-hmm.
Some of the questions are asking for getting the distance from where the force is acting on,
Mm-hmm.
and that was a thing I don't remember.
No problem.
Could we go over that again, a refresher, or?
You know it, but you think that you don't. Hopefully this will show that you do. Moment is force times distance, right? We can agree on that. And the sum of moments on a system will be equal to the sum of all of its forces times all of its distances, right? So when we say an average force, what we do is what's called reduction. So when we say reduction is when we have, let's say we have all of these forces. Instead of looking at each force individually, we will reduce our forces, okay, into one force. So for example, I have a 20-pound force and a spring force. My total forces in the x direction is 50 pounds. So if I want to reduce these two forces, what I can do is I can express them as only one 50-pound force instead of a 20-pound force and a 30-pound force, right?
Okay.
So it's easy linearly, right? So I can reduce my forces to a 50-pound force, but in order for that reduction to be complete, I need to figure out if this 50-pound force can cause an equivalent moment. It's actually not that easy. Let's go ahead and look at it, okay? So I'm glad you brought this up because it's good to have it on the video so that all the students can see. Let's say I want to reduce, right, the x forces in this system. We got a 30-pound force and a 20-pound force. What does this reduction have to give me? Well, first, my reduction has to equal the magnitude of the forces. In other words, my reduced force, I'll just call it Fx. My reduced force has to be equal to the magnitude of 20 pounds and the magnitude of 30 pounds. So my reduced force has to have a magnitude of 50 pounds. If it kind of rings a bell, remember, this is what we call the net force, just the sum of all the forces. If this were a 20-pound force towards the left, what would this reduced force equal?
That would reduce down to 10 pounds.
Exactly. Okay, so you're adding the magnitudes up, considering the direction. However, I need to figure out where in the system am I going to place this force. So I have, right, a 50-pound force, but the question is, where do I put this force? I need to put this force wherever it causes the same moment about the hinge as the other two forces combined. So I look at my two forces, and I say that my moment about the hinge is 20 pounds times 2.5 inches, negative, minus 30 pounds times 1 inch, right? That means that the total moment is, can you give me this number again? This was 20 times 2.5, 30, well, minus 30, okay?
Negative 80.
Negative 80, okay. So we got negative 80 pounds per inch, okay? So when I reduce my force, this 50-pound force has to result in a negative 80 pounds times inch moment. And the question is, where, I'm going to call this D, at what distance D do I have to place the force to cause this moment? Well, we go to our definition of moment. Moment is equal to force times distance. I know the moment that I want. Do I know the magnitude of the force? Yes, 50 pounds. So I solve for distance. Distance is equal to moment over force, negative 80 pounds per inch. And here you want to be careful with your signs, because in terms of distance, this negative means nothing, really. Okay? So 80 pounds per inch divided by a force of 50 pounds gives me a distance of 8/5 inches. How much is that?
1.6.
Okay? So that means that this force has to be at a distance of 1.6 inches, somewhere in between these two, as you can see. Okay? So that's reduction. You want to make sure that your forces cause an equivalent, an equivalent effect, not just in magnitude, but also in moments. We're going to talk a lot about that later, so don't worry too much about getting it right now.
Okay.
Right now, I would like for you to focus on how to balance systems before we work on reductions. Okay?
Got it.
Any questions with this? This is a bit off topic, I agree, but it's good that we know. I mean, we're going to cover it in detail later, but it's good that we at least have an idea. So, we're good with this? Okay. When does this class end?
47:45.
Okay, so we still have a bit of time. Good. I'm going to skip a little bit. I'm going to leave section 5.4 for later. I'm going to skip all the way to section 5.7. We mentioned that this system had a hinge which only provides an x and y reaction but no moment reaction. Now, if we want this system to be static, our goal is for this system to not move. You may think, right, from a design perspective, we can turn this into a fixed support, and then we can guarantee that it won't move, regardless of forces. So perhaps you may think that from a design standpoint, from an engineering standpoint, you want this to be static, make this hinge into a fixed support. However, you'll see that turning this hinge into a fixed support is not helpful for us. Because if this hinge were a fixed support, then this system would become statically indeterminate. And what do I mean when I say statically indeterminate? What I mean is that applying the equations of statics cannot help us solve the system. So let's look at an example. Let's say that we turn this hinge into a fixed support. So the fixed support has an x reaction, a y reaction, and let's say that it also has a moment reaction. Okay? And now I apply my equations of equilibrium. I know that if I apply my equations in the x direction, I can get the spring force. And I know that in the y direction, I get that F equals Ry. So now when I apply my sum of moments, of course, I have my F times 5 inches, positive. I have my 20 pounds times 2.5 inches. I have my 30 pounds times 1 inch. But I also have the moment reaction. How many unknowns do I have in this equation? 2. So I cannot solve for either unknown. So even though it seems or it makes sense to say, if I want this system to be static, add more reactions to keep it static, what I'm doing, even though I'm adding more reactions, all I'm doing is making my equation harder to solve. Not harder, impossible to solve. Okay? So from a design standpoint, you need to be careful. Because some systems may have more supports than needed to keep it balanced, and more supports than needed means more unknowns than equations, which means that we cannot solve it. A system such as this, where it has a fixed support, is a statically indeterminate system because we cannot find the forces or all the forces and reactions in the system using statics equations. This section is more as a warning, right? Sadly, we can't use our equations to solve for everything. Okay? Perhaps if you have a system where you know your forces are distributed equally, maybe we can come up with something. But right now, right, in this system, we have two unknowns, but only one equation that relates them, so we can't solve it. So if I were to give you this system, let's say on the test, if I were to give you the system with a hinge here, and I say calculate the forces, what's your answer going to be? We can't.
It does not exist.
Yeah, we cannot calculate those forces because it's a statically indeterminate system. Now, if I really wanted to mess with your brain, I would give an option in all the questions saying it's a statically indeterminate system. And if I really wanted to mess with you, all the answers would be statically indeterminate. But I'm not going to do that to you. Okay? Or maybe I will. Yeah, who knows? I'll think about it. It depends on my mood. I actually think we can finish the chapter today. We still have about 10 minutes left. So let's go ahead to section 5.4 and talk about 2 and 3 force members. I recommend that you don't worry too much about this. Essentially, the idea is if there are more unknowns than equations, you can't solve it. That's it. That's all it is. So I wouldn't expect you to solve it, but I'll expect you to know if you can solve it or not. One caveat, sometimes we can relate forces to things, right? So for example, you had that one problem where you had a spring, right? A cable, a force P, and it asked you to find the angle theta. And that problem, we ended up with a couple of unknowns, right? S, phi, whatever. Actually, that problem was not statically indeterminate because you could actually relate, different variables to each other. So as we start to progress, we're still not there yet. But once we get more statically mature, that we can actually look at harder, more complex problems, I'm going to try to guide you into identifying the statical determinacy of problems. But for now, all I need you to know is that sometimes a problem may not be able to be solved, and that's okay, right? That's okay. We just need to figure out other methods. I'm going to spend the last 10 minutes talking about 2 and 3 force members. Possibly just 2 force members. If an object only experiences forces at 2 ends, we call that object a 2 force member. So let's say we have this object, neglect its weight, and this object only experiences a force, reaction force on this end, reaction force on this end. What we have is a 2 force member. And why are 2 force members important to us? Let's say that I call this my point 1, or A, and I call this my point B. This is my reaction, or my force AX, my force AY, my force BX, my force BY. First off, just as a general vector question, what is the magnitude of the total force A? Just the total force, the combination of these two, what's its magnitude? Right? Okay. So I know that these 2 forces will result in a resultant force that I'm going to call A, oriented at a direction of inverse tangent AY over AX. Can we agree on this? This is from chapter 2.
Should those be squared values? Sir?
That's absolutely right. Can we agree on this now? There we go. And then we can say similarly that B is equal to the square root of bx squared plus by squared, and that B acts at an angle of inverse tangent by over bx. A bit of a review from chapter 2, right? Okay. Now, if I were to apply the equations of equilibrium into the system, here's the fun thing, right? Let's say this is B. If I were to apply the equations of equilibrium, let's see, I have sum of forces in the x direction equals
0.
Okay. I have force AX. I have a force negative BX equals 0. So AX equals BX. Because it's a two-force member, these are the only forces acting in my system. They're equal to each other. But notice that they're equal to each other by acting in opposite directions. Y direction. Sum of forces in the y direction equals
0.
I have my AY. I have my BY equals 0. And I get that AY equals BY. If AX is BX and AY is BY, if AX is BX and AY is BY, can I say that A equals B?
No.
Yeah, no.
Yeah, right? It's the same number, right? The same number squared plus the same other number squared. Take the square root. It's the same number. So what do I get? A equals B in terms of magnitude. And if you look at the directions, notice that AX is simply in the opposite x direction of B. AY is in the opposite y direction of B, which means that my resultant will be in the opposite direction. So angle B, right, will be equal to angle A plus 180 degrees. So what does this tell me? For two force members, the two forces are going to be equal in magnitude, but opposite in direction. Okay? So both forces are equal in magnitude and opposite in direction. So this is a two-force member. And hopefully you can see how we identify this two-force member, or why we would want to care about this two-force member, right? Because this two-force member, what this tells us is that both forces will have the same magnitude. So really, if we can find one, we will know the other. And then we'll have different magnitudes. So that's pretty much all I have to say about two-force members, really. We're going to go over an example, but I have 6 minutes left. I personally don't think 6 minutes is enough to go over an example. So I'm going to stop it here. Okay? I guess on next class I record, I guess the Wednesday class, make sure you watch that video so we can go over a two-force member example. Are there any questions before we wrap up? I know it's a little bit early, right? 6 minutes early, but are there any questions? Jared? Chris? Graham? Noah? Tuong? Luis?
Yeah, no questions.
Daniel? Sophia?
I'm so confused with the angle because if the angle B equals angle A plus 180, that means they're not the same numbers.
So you want to be careful when you're looking at your inverse tangents, right? Because an inverse tangent, you say that tangent of the angle is y over x. This actually only applies, right? This actually only applies to the first quadrant, right? So in this case, if you look at what we're having here, notice that we have AY, AX, they're both in the first quadrant. But BX, BY, they're both in the negative quadrants, right? So we have our quadrants, 1, 2, 3, 4. AY, AX, since they're both positive, is in the first quadrant. Just use this equation. If they're both in the third quadrant, then the angle will be equal to the inverse tangent. Inverse tangent of y over x plus 180 degrees. If it were on the second quadrant, it'd be equal to the inverse tangent of y over x plus, what, 90 degrees? Yeah. And so on. Okay? So we want to be careful with your inverse tangents here, because remember that this equation, tangent of theta equals y over x, only applies for the first quadrant. So all I'm doing here is I'm applying a correction saying, well, this is actually in the third quadrant. That's all I'm doing. Kevin? You good? Did that answer your question, Sophia? Okay, so I guess I'll let you go. I'll see you next week. Have fun.